first of a couple of topics related to coding. This is one which every year I find that there's incomplete recognition in the course of the term of the importance of error handling within this course. And more than that, beyond just sort of not handling errors, it turns out that errors of different sorts are handled in sometimes inappropriate ways. And my intention in giving this lecture early is to make sure that you have the tools you need when you're starting up coding in the first phases of your project to put in place solid code with respect to unexpected events, with respect to programmer errors, and to signal indeed whether pieces of your system have worked or not. So today's lecture, we're going to be talking broadly about this issue of how to handle situations where things go bad. Things don't go per expectation. They don't go according to plan. Yes? Okay, well, that would, that was supposed to be assertions, the last one. Yeah. Yeah. Thank you for catching that. That's great. An assertion. Yeah, so we're going to be talking about 3 different ways within today's lecture in which we handle and indicate situations where things have gone wrong. And a reflection to take into account here is that in building software, we're frequently focusing on sort of the normal case, the typical case where the work's going to get done. And for each of your systems, this might be a different case. For the case of the survey system, this might be a situation where the user, one after the other, fills in the elements of the survey, and survey scores can be calculated perfectly well, and perhaps even that it can connect to a network and send the information back to the mythical Postgres database. For the case of the patient simulator, maybe this is a situation where the system needs to interact with the user, and the user responds as expected, pushes on buttons within the expected period of time to indicate, for example, that they've been reminded successfully, and that dialog box can go away. However, things sometimes go wrong. Well, handling the sort of typical case is often the goal of the software, the direct goal. It's perhaps the case where we see the value as being delivered. Often it's just about as critical to handle cases where problems arise. In some cases, handling these can be mission critical. For example, security issues. Situation where you get something pasted into your search box within a website that's full of SQL code. It's not what you expected, it's not what you wanted, it's not what you built the system to handle, but you sure as heck have got to be able to handle it. You got to be able to handle it and respond to it effectively. In other cases, there's end user errors. They interact with the device or with your system in unexpected ways. They accidentally click on a button twice. They don't fill in a field that's actually required. And your system needs to be able to handle that. It needs to be able to issue an error message. It needs to be able to warn them. It needs to be able to leave gracefully and say, I can't connect, for example, to the machine you've specified to me. Please retype the name. In other cases, it's issues of resource failures. When I was a young man, when I was your folks' age, and that was once the case, things were simpler. When we built programs, typically the programs were to run on the same computer. And they didn't have to go out over the network. They rarely went to other devices like printers or disk drives directly. And there were fewer dependencies on external factors. They didn't depend on a website to get information, to get the current temperature in Saskatoon from a website. They didn't depend on a database that was located on a separate machine. They didn't depend on other processes, typically within the same machine. They were self-contained. The world's gotten a lot more complicated than that. And as Dave Gifford once said, one of my professors in grad school, you don't want the World Wide Web, distributed computing, to mean that every time someone off across the country unplugs their web server to move it, your system crashes. You don't want this huge interdependency we see, which erases all these opportunities for us in terms of creating sophisticated software, to mean that our software is brittle, that it breaks easily. We don't want the ability to get information from lots of resources to hobble us when those resources aren't available. Or at the least, we want to be able to gracefully handle that situation, not simply end up with a corrupted data on disk because we haven't been able to write the full set of data because we haven't been able to go over the web to get to a certain database or what have you. So, you know, more than that, sometimes you're going to need to deal with corrupted data. In a real-life system, you may be opening documents which will sometimes have been corrupted. What sort of processes would lead to corruption, despite your best efforts? No fault of your own. What could lead to corruption of data? Yeah. So it could be that there's an error on the disk, for example. Disks fail over time. In my time, I can ask my wife. I have this big tub of failed disk drives down in the basement. I probably have 20 of them that have failed. Some of them have failed catastrophically. Some have spent days trying to recover information from it. I was backing it up every day, but I would ignore that warning error because I thought it was something about the file name being too long. Oh, surely that can't be serious. And then I discovered that when the disk crashed, that meant that only a few of my files were backed up. So I spent days trying to recover them. So disk drives fail. Other things fail as well. Connections fail. Memory sometimes fails. Sometimes things like thumb drives fail. Anyone here encountered a thumb drive that's failed before? Yeah, so sometimes they fail silently but deadly. Sometimes they fail in really obvious ways. So I sponsored a conference about 5 years ago, this July, and we handed out thumb drives as part of the conference with the conference logo on it. And one of my students pointed out that for some of these, they were faultily manufactured, so if you stuck them in and you pulled them out, just the outer sleeve would come out and the circuit board would stick in there. Bad things can happen. And of course, your static electricity could get on it. Static is another nasty thing which occurs. Anyone here an engineer? Engineer by training? Anyone coming over from School of Engineering? No? Okay, so I'm an engineer by training, and let me tell you, we live in an analog world. We live in a world that we have this digital abstraction, ones and zeros, but occasionally it breaks down. And occasionally static is unleashed. And it can damage memory. It can damage processors. It can damage other types of hardware. And sometimes these things are quite dramatic. I remember one case where a student of mine was working with a piece of hardware, and he said, it was in the winter, and he said what looked like a fireball came out of his hand, and it destroyed a car. And I've seen sizable sparks, and I've seen things fry because of that. Things fail. And we need to go through building systems as if things will fail. It's all well and good if we're just building it for ourselves to use occasionally, and we can test whether it's working or not, perhaps to let things slide. But if we're building things for other people, we're going to count on it. We need to be ready for things to fail. Phones fail. Phone GPS systems conk out. Lots of problems. And then finally, there's a type of error that we don't like to deal with much, but it's a reality. It's a reality for me with my own code. It's a reality for everyone in this room, and it's a reality for the industry. We have oversights. We have reasoning failures. We're inconsistent. We may put a specification in that this method needs to take a non-null value, and we end up, against our best knowledge, passing it a null value. Maybe it's returned by another library, which we're depending on, and we didn't know it could return null, but it does. And suddenly, we're in trouble. So how do we handle it when things go bad? How do we handle situations where things don't go as expected, where there's problems? How do we deal with these inconvenient cases? Just asking that question is a step forward. And unfortunately, often within this class, I find student code that hasn't even asked that question. Has anyone in here seen code where you have a try-catch block and the catch statement is empty? Yeah, maybe, you put it in there and maybe you think it's a temporary thing, and then you go to lunch and something else interrupts you, and you forget that it was in there, and you don't come back to it, and it's still there, and it doesn't handle it properly. In this class, when I look at code, I'm going to be judging a lot its maturity by asking, does it handle things in a mature way? And today's lecture is about trying to communicate to you some basic rules of thumb for how to handle things properly. Because often I find, it is being handled, but it's being handled in the wrong way. For example, we're saying memory is always available. Disk space is always there. And that's not true. So I have programs available to me which can make your program, it makes it seem as if there's no disk space left. So if your program's making assumptions that disk space is always available, it could run into real problems when I go to test your programs. So both for testing and for sort of, from a standpoint of being careful as a general principle, you want to be able to handle these conditions. And there's three broad ways that I'm going to be talking about today of handling these conditions. If necessary, we'll go into next time, so it's important material. One is to indicate it with a return code. What do I mean by return code to signal an error? Anyone? Yeah, return -1 to indicate failure, for example, or success. And what 0 means will differ a lot. Can anyone tell me a situation where a 0 means success? Yeah, exactly. Exit status on Unix systems, right? Unix and Linux. Standard. In many other cases, a 0 will indicate failure and a 1 will indicate success. So it indicates, did it succeed or fail? But return codes are very widely used to communicate things, and often encoded in numbers. They're codes. They encode this information, okay, numerically. A second mechanism we'll talk about is exceptions, and the third one, the use of assertions. I think these first two are going to be familiar to you how you go about using them, but what I want to hit on is when they are used, for what purposes they are used, okay? That's what I want you to take away here. I don't think I could teach you how exceptions work, although there may be one or two twists that I may emphasize. Assertions, on the other hand, are something that I recurrently see students not putting into place without explicit guidance. And this I would like to see littered all over your code. Okay? I want to see assertions just used, you know, there should be, in many cases, something like a 5-to-1 ratio of main statements to assertions or less. So in other words, the number of assertions is a large fraction of all statements, okay, in some cases. Not all, but in some cases. For very short methods where you're just checking the parameters and doing something very simple, you actually may have several assertions for a small method. And we're going to be talking about how you go about using assertions in Java because it may not be familiar. First, we're going to be talking about return codes. Okay. So what are return codes? What do they involve? They involve encoding, typically in a numeric fashion, common conditions which are frequent enough that we need them to be quite fast. Performance needs to be considered very carefully. So these are cases where we know it's going to occur typically at some point or another, like an end of file. If you go through a file, there's going to be an end of file. It's a common case. You know it's going to occur in this case, and you want to be able to handle it. You want to indicate it, but you don't want to do that in a very heavyweight sort of way, as we'll see is the case for exceptions. Last item in a linked list. Item not found in some data structure. So, you're looking up in a dictionary and you can't find a certain key and it needs to return what? What would a data structure return if it can't find a key? Say a dictionary. Null. Might return null. Right. So that's a case of a return value, right? That's being used to indicate, hey, I couldn't find it. Okay, so what are some advantages here? Well, main advantages are that it's lightweight and simple to use. Conceptually straightforward. There's a set of other disadvantages, though, that are pretty significant. Handling is not enforced. There's nobody saying, you need to handle that. Zero. That, no. Right? Secondly, there's risk of inconsistency. I could interpret a 0 one way, and Jonas could interpret it a different way. I may think a 0 is an indication of success, and you may think it's an indication of failure. I've worked in situations like that within the past year. I see this code being returned. I don't know, is that success or failure? Not sure. So there's inconsistencies in how different parts of a program may use a certain value, and risk of misinterpretation. And finally, there's no metadata capture. There's very little opportunity here to pass back substantive information about what went really wrong. Maybe it indicates failure, but it doesn't say why it failed, at what stage it failed, how it failed. It doesn't say how far it got, the exact nature of the problem. So maybe this is a routine which tried to connect to a database, and it returns 0. You don't know what that means. Does it mean there's a it doesn't know the database server name? Does it mean that it tried to go over the network and it couldn't connect to it? It found it, couldn't connect. Maybe there was a DNS error, domain name server error, and it couldn't even find a resolution of that name into an IP address. There's all different interpretations, and it's hard to pack those into return codes. You can maybe make return codes for a couple of them, but if you really want to pack in additional information, like where in the code this problem took place, it's hard to do it. Now, partly to deal with some of these problems, we can use a more sophisticated mechanism. So how many people in this room have used enums before? Okay, most. I'm happy to see that. Why do we use enums? Why not use ones and zeros, twos and threes directly in our code?
Clear what the zero, that number what
That's absolutely key. So thank you. Your name? Wei Zhong.
Yeah.
So as Wei Zhong said, it's clear what a 0 or 1 or 2 means. And very importantly, it may mean different things in different areas of the code, and the compiler will actually check. Okay, here we're using name of a province. Here we're using a 0 to mean a sex, say male, and it makes sure they never mix together. This is really important. If you just decode it as 0 or 1, say for sex, and 0, 1, 2, 3, 4, up to 12 for province and territory, what's to prevent you from assigning male to province? It's meaningless, but they're both 0, and you can use it, or both 1. Here it's clear. Someone reading the code, if they see it, they see the name, NB, they know it's New Brunswick, or they see it spelled out New Brunswick, or they see it spelled out male. It's clear what that means, right? And it also prevents you from assigning one to the other, just mixing them together. There's actually a semantic check. Are you doing something meaningful? If there's a method you write that takes in a province as an argument, as a formal parameter, and you pass it a sex, it'll say, I don't know what that is. If you have a method that takes in an int that's supposed to represent a province, and you give it a 0 that happened to encode a sex, it would happily take that. It doesn't know there's anything wrong with that 0. With enums, it will actually do the work for us. It will check things, okay? So it leverages compiler checking. And as Wei Zhong said, this allows us to assign meaning to particular values. Without enums, it may not be consistently used, it may not be clear, and this allows us to be clear how we're using these names. Now, in languages like C, we don't have the luxury of defining an enum, and so often we pound define, things like OK, EOF, and we at least use these in our code. What's the difference between this and an enum? Does this give all the benefits of an enum when you're using these pound defines? Exactly. Yeah, I mean, as far as C is concerned, OK is an int. And you could pass it to a routine expecting a province encoded as an int, and it's going to be perfectly happy. So it doesn't give you the compiler checking. It does make it clearer than using a manifest constant, using just a constant in your code. We're going to get to that later. And that's an important principle that these also help with, things like enums and the C code. They help with that. They mean you don't just mention 0, -1, 999 in your code. But with macros, it isn't checked. It isn't checked as formal. The compiler doesn't confirm for you you're doing something meaningful. You're giving it the type of information it needs. Does that make sense? Now, it turns out enums in Java give you lots and lots of other benefits we're not going to be talking about here. You can give them nice toString functions. You can have maps that map them to different values. You can declare what their actually numeric values are. So maybe you want to make it 0, 1, 2, 3, 4, 5, up to 12. But maybe you want to have them be powers of 2. So you can and or them. So you could say New Brunswick and Saskatchewan, and them together and get out a value. So you have them encoded as powers of 2. You can do these sort of things with enums in C++, and Java, and other languages. So enums are good things to use. I hope one of the things I don't want to see in your code bases is manifest constants, and one of the things I do want to see a lot is use of enums instead. Are both teams here planning to use Java? Okay, JavaScript. Okay. JavaScript is even more flexible than Java in some regards, but you'll certainly want to avoid using so-called manifest constants, which are just numbers. You want to make sure they're associated with a meaningful name. Okay. Another principle here is you want to explicitly handle all values of these. So when you have, say, an enum or other implementations of return code, make sure you handle all possible values of it. So you're explicit that you're handling all possible values returned. An important difference from some other cases we'll be looking at is the compiler won't automatically enforce that. It's kind of up to you to handle it. But as a convention within your team, make sure you always handle all cases. You don't want it to just not have a handler in a switch statement and therefore not know what to do with it and not do anything. And typically, as a matter of offensive programming, of going out and trying to find bugs rather than letting them find us, we want to define default values of, say, enums to be illegal. So if it's a 0, say, and if memory is initialized to zeros by default, or if values are put in there by default, we know it's some illegal value. It hasn't been initialized yet. Does that make sense? In other words, you give it the default value for a variable that has an enum should be something that's not a true encoding of anything. And it will require you to assign to it to give it something meaningful. And this will make sure that you don't forget to assign to it. Make sense? This is one of the dangers. If you have memory initialized to zeros, and 0 encodes OK, and you see a 0, you don't know if that's real indication it's OK, or if that's just the default value, you forgot to initialize it. That element of the array never got information put in it. So you make the default value illegal. Is that clear to people about why we do that? Yeah? Okay. So that's a matter of sort of hygiene and best practice. That's a matter of offensive programming. So we talked about return codes here. Let's contrast them with exceptions. So I want to contrast here the cases that we just examined for return codes where we have commonly needed items, the commonly needed conditions, things like end of files, last item in a linked list, the dictionary item not found, those sort of things. I want to contrast those with situations which are uncommon and rather exceptional. They're not guaranteed to occur. Here, if you go through a linked list, you'll eventually get to the end. It's going to be fairly common in many cases to not find something in your data structure. The end of file is going to eventually happen. It's a common enough case that to make it expensive would impose a real problem. On the other hand, sometimes there are situations that are really quite uncommon, but we've got to be able to handle them. Why do we have to be able to handle them? Because they're not under our control. What are some examples of those things? Memory is exhausted, disk is full, network is unavailable. Some attempt to connect with a server concept, there's a broken connection, it's a corrupt file. Files are not found on disk. Maybe the user moved it. Data corruption. These things are not under our control, right? We can't control this. Can't control whether the disk is full or not. That's outside our ken. We don't have the ability to control that. And yet we have to handle these situations. And for these situations, ladies and gentlemen, they tend to be not common. You could argue that some of them, like memory full on certain systems, particularly embedded system, is not totally uncommon, but it's not it's not so common that we're going to be taking a huge performance hit if we have a little bit of overhead associated with these things. Often, some of these things may require expensive cleanup. We're out of memory, we may have to free up some data structures in memory and gracefully leave. We're out of disk space, we may have to back up what we've been doing and leave the program. So let's talk about how to handle these cases, and the particular mechanism that's recommended for these rare, uncommon, inconvenient, but necessary things that we have to handle is exceptions. Exception handling. Okay. The key need here is that we need a way to indicate that things have gone wrong in the execution of code. And sometimes we'll handle it right there, but sometimes we'll delegate it. For example, to those who have called us. We don't know how to handle it. We're just a small routine that tries to connect to a database. We don't know how to handle it if that database is not available. It's the people who asked us to connect to that machine that have to handle it. It's that code that called us. Maybe, we've been asked to find something in this data structure that should be there. We can't find it, but folks who built the data structure, the code responsible for building the data structure is somewhere up there, called up down to us. We need to delegate back to it and say, hey, you go up and handle it. Okay, so we need to go back to a context where we know how to deal with the error. Human situations are like this a lot. We encounter a situation we don't know how to handle, and I may go talk to my department head, or I may go talk with my dean. I don't know how to handle this difficult situation. Half of the final exams were burnt up when my house burnt down. What do I do? I don't know. These others they're charged, but I was able to mark them. But half of them are toast. What do I do? I go talk with my department head, who you might say, well, beats me. Go talk to the dean of undergrad education. So then I go talk with the dean, and he says, oh, we had a case like that 25 years ago. And we gave everyone 100% of my class. No, don't burn down my house, okay? Remember, I don't know, maybe he'll say we give everyone a 0. I don't know. Well, I'd say, I'm not going to stack. In any case, the point is that in human systems, we delegate. We go back up our sort of level of command. The idea is that as you go down in a call stack, it's that, A calls B, calls C, calls D. Often it's becoming more specialized. And the things that called you are often more general. And so you kind of go back to them and you let those more general things handle it, right? Okay. And in Java, of course, we signal exceptions. And we throw them at some place, and then they're caught in various handlers. And I think all of you have seen this before. You've probably worked with this. So we have tried catch blocks, right? And this is important, folks. Make sure you try to take advantage of having, you can have multiple catch blocks. This doesn't have to be, catch exception E. This could be like catch null pointer exception, catch out of memory exception, or what have you. Different types of conditions can be given specialized handling. Because some of them you might know how to handle reasonably. Others you might not. And so you might have a very general one at the end. Great. But more specialized ones, why not try to handle them if you can? Okay? The file is not found. Okay, then you create a new file. That'd be a sort of a classic case. But we might not know how to handle in this little routine, we might not know how to handle a disk corruption error. And so we end up throwing that exception up, letting that propagate upwards, okay? Now, an important component of this, how many people here have used finally blocks? Okay, good. So you've been trained, you saw this in 270? Okay, good. So finally blocks will have some common set of code that's to be executed either at the end of going through successfully through the try block or at the end of any exception. Right? It does this last. Whatever it's doing, it cleans up kind of thing. What sort of things might we put in a try in a finally block? I haven't seen them much in student code for this class, so I'm delighted to hear you folks have faced them. What sort of things might go in there? Remembering. Close. Excellent. So in general, clean up resources, right? Memory's a resource, files are resources, database connections are associated with resources. Sometimes connections to other machines are associated with resources. These are all things you got to kind of clean up so you can leave out of this, this context. And if you don't do that, you end up in one of two situations. Either you need to repeat that basic code in all these different exception handlers, or you end up leaving it out and you get a file that's half written. In other words, corrupt. Half a file. How does your program load it in the future? Half a database record is not transactional. Half of the information transmitted over to the server and the other part not. So, so we want to use finally blocks liberally. So, okay, you've seen those things before. So what are the drawbacks with exception? These are nice things. And by the way, I should emphasize, these blocks here, they will frequently rethrow the exception. So suppose you catch an exception here. Sometimes you'll throw another exception if you can't handle it properly, right? Look at it and you try to figure out what to do, and sometimes you'll rethrow it from here. Sometimes you just won't catch something here. And what happens if you don't catch the exception type here? What happens to it? No, it actually delegates automatically to the next level that called you. But your method is for at least statically checked exceptions, which are an important class in Java. Your method has to say throws such and such. So your method will say something like throws, class not found exception or something like that. And that's required because someone who's going to use your code needs to know that, okay, one of the ways that your code could come back is with an exception of this certain sort. Does that make sense? Okay. Now, I should note, in Java, there's broad class of exceptions, statically handled exceptions, as compared to a set called runtime exceptions. And an important difference is that for static exceptions, either if that can occur in try, if there's an exception that can be thrown by this try block, because you're calling off some routine, you're calling something in the Java library, you're using a file object and trying to read in information from it, and it can signal a file not found exception. Either your code has to handle it, or your code has to say it throws it in its method declaration. Does that make sense? Are people comfortable with that? So, when you declare a method in Java, what do you specify when you declare a method in Java? What are a few things you have to specify according to the compiler? Okay, so some sort of return type, good. It might be a reference to a class, it might be void, some sort of return type. What else? The name, good. And other things? Argument names and types, excellent. And what's another thing? Visibility, okay, so whether it's public, protected, private, all those sort of things. Whether it's final, right? So those various qualifiers and so on. But the other thing that you will sometimes have to declare is throws certain exception names. Because if you have this try block and it's calling certain routines that will throw these statically checked exceptions, either you have to handle them in your catch statements, you have to clean up after them, or you have to tell whoever's calling you when they're writing code against yours, they need to know, hey, this method could throw an exception, because if it's not handled here in the catch blocks, it goes up to whoever called us, and they need to be ready for it. Does that make sense?
Is that like checked out?
Certain, yes, for a broad class of exceptions to check, statically checked exceptions. There are, however, this is a great question. There are, however, a set of these sort of exceptions that are not checked by the compiler. And those are called runtime exceptions. And those exceptions you don't have to declare up there, and it's not going to make sure that someone handles them properly. If someone does, great. Great, it'll let them handle it. But those exceptions, it's not going to take care of watching out for you that you've handled them here or that you've declared that they're handled. There's a significant dissension within the software engineering community whether forcing people to handle exceptions, like statically checked exceptions, is good or bad. How many people here have struggled against statically checked exceptions before? Okay. Yeah, I think a few of us. Okay, yeah, so oh man, we know it's not going to occur in this case. We think it's not going to occur in this case, and yet we have to put in a catch block, or we have to say we throw it, and then we have to go change our code elsewhere to throw it in. But it's a matter of being, I mean, it's a nuisance when we're building code for ourselves or just for small projects. But if we're building code for clients, we want to be able to handle, you know, disk full errors or what have you. And so we do have to be kind of careful about these things. Okay. So that was some things about catching these things and so on. What are the disadvantages of these? So, good. This is, it lets you, explicitly catch it when things go wrong. When you throw an exception, you can wrap up all sorts of useful information with it, right? When you throw an exception class, you can design your own exception class. How many people in here have built their own exception class? Okay, yeah. So you can create a custom exception class. You know exactly what it means, what sort of condition it signals, and you can put all sorts of information in it, right? The constructor can take all sorts of useful information. The line number where it originated, who is responsible for that code, the time at which it occurred, other aspects of the context, what it was in the middle of doing, all sorts of stuff, right? If you want to, you can wrap that up in the exception. Ain't that good? It's better than return code in the sense you can wrap up all these metadata about what it is. You don't just say, this bad thing happened. You say, this bad thing happened, and this is the information you need to know how to handle it or to make sense of it or to return the requisite information back to the software company that built this software or whatever. So they're great stuff. What's the shortcoming of them? Yeah. It's overhead. And I don't want to overplay this, but it comes at a significant performance cost. The reason I don't want to overplay this, for occasional things, it's not a big deal. Look, if you run out of disk space, even if it's just Osgood running that software program, it makes it seem it's out of disk space. It's not a big deal if your program takes, 0.0125 seconds more to return back. It's just not a big deal. However, you don't want exceptions thrown in an inner loop of your code that's running over and over again, thousands of times. And there are cases where exceptions can impose overhead if they're constantly occurring. That is not how they should be used. They should be used for these sort of rare types of events that we know we have to be able to handle, but they're not common. In some languages, particularly C++, exceptions can lead to memory loops. Why? What bad thing could happen if we handle an exception? Yeah. Exactly. So in C++, you're not going to be using a garbage collector. You got to allocate memory. You got to free it. People comfortable with that? How many people here have used calc or malloc? How many people here have used new and delete in C or in Java? Yeah. Okay. Oh, I'm sorry, not in Java. C++. In Java, how many people in here have used new? Okay. Yeah. Basically everyone. Good. How many people in here have done serious amounts of C or C++ programming? Okay. So one of the big differences between how you spend your time in C++. So I've written hundreds of thousands of lines of C++ and maybe hundreds of thousands of lines of Java if you go back and check. Done things in a lot of different languages. Certainly in C. Huge amount. And one of the big ways that you discovered is different in how you spend your time in Java versus these languages. A huge amount of time, in my experience, for C and C++ goes into debugging memory leaks and errors with loose pointers and weird Heisenbugs where occasionally, it runs fine under the debugger, but if you run outside the debugger, it works, it crashes. These things are disconcerting. I remember one bug I was working on for 2 days, just trying to track it down. Where was this memory problem? Loose pointers, situations where a pointer, we think a pointer is good, but it's pointing to nothing meaningful. Maybe pointing on top of something else. We deallocate it and something else has been allocated at that same place, but we're still using it. Bad news. And in C++, we have exceptions, but we also have this manually, we allocate memory and deallocate it manually. And one thing that may happen is we have a reference, the only reference to a piece of memory. We've allocated it, we've done new on it, and normally we run through this code and at the end we delete it, right? Does that make sense? Normally in our routine, we do new up top, right? This is some method foo, and here's a bunch of stuff, and we set this pointer to be new of some a new student, and we have some arguments for the constructor, and we use it, and various things going along like writing it to disk or whatever, and then so we have various things referring to P or P, their name or whatever, manipulating it, frobbing it, and then at the end we have delete P, right? Yeah? Or maybe we knew an array and we do delete bracket to the array, right? Okay, now, this is all fine and good. Great stuff. We allocate it here, we deallocate it there, we're disciplined, we're wiping our butt. But we haven't wiped our butt enough, because what happens is we can bomb out of this middle place. And we go out to an exception handler down here with a catch, and if we don't clean up our memory here, if we don't deallocate P, it stays allocated, right? We never got to this place. It bombed out here due to an exception. We end up here, we forget to clean it up, we just print a stack trace. How many people here have written in Java, exception handler, it just prints out a stack trace? Yeah, okay. Fair enough. We're all in this together, folks. But the fact is, when we comes time to deliver to a client, we should be handling carefully the errors that we can. And if we can't, printing a stack trace is okay, but you might want to think about something more sophisticated. If you don't know how to handle this thing, at least clean up the resources and probably, ideally, send a message back to the mothership. You send a message back to the server and say, this bad thing happened. this bad thing happened. And this is all the information about it and includes the stack trace. And then it at least allows it to be recorded on the server. You can go back and say, oh, okay, that error occurred to Hassan, eh? So he was doing it on a cell phone, and it died in the middle of printing the survey, or what have you. Send the information back. Okay, so some languages, what I'm saying is that if you have an exception go on, languages that are not garbage collected, you have to be very careful because it can lead to a memory leak. P is not deallocated. But in Java, you don't worry about that. Why not? Because it's garbage collected. Thank you. It takes care of actually cleaning up that for you. Okay. Another drawback of exceptions, people commenting on sometimes, it's hard to recognize certain mistakes in the code. Looking at this code, it may seem like straight line code. If it gets here, it's definitely going to get here. Oh, there's no if statements. It just goes straight down. So it's easy to think, oh, well, we're always handling it correctly. But if it can bomb out of there, sometimes you'll miss certain logical conditions where certain variables are uninitialized still, and later you use them. There can be some problems with breaking of subtyping rules. We may get to that later when we talk about Liskov substitution principles. So languages that provide finally blocks, garbage collection, and sometimes forced declaration for certain types of exceptions, for so-called checked exceptions, can be useful. The main issue I want you to remember, though, is if it's a very common event, exceptions may impose a high overhead. At least you should study it with a profiler. How many people here have used a profiler before? I'd like to suggest everyone, there's some wonderful profilers out there that are incredibly simple to use. And I'll see if I could show one in class sometime. But, test it. If you're not sure, you could test what's the overhead of this exception. Generally, exceptions are great stuff. You just want to be careful about how often they're thrown at runtime. If it's occasional things like a disk being full or out of memory, all that sort of stuff, yeah, sure, use exceptions. That's going to be a minor part of the whole thing. Okay, a couple other suggestions with exceptions. Translate exceptions into meaningful languages. So in other words, if it's coming up to a certain level, a user like Jenny Basran or Hassan is not going to want to see an error message that says, the key associated with, or the value associated with key such and such in the hash table is null. It's not going to be a meaningful thing. It's not going to be meaningful to talk about a null pointer exception. So you want to at the least translate this into something meaningful that at least is not scary, right? So something bad happened that we can't correct for. This program can't save its data. Please contact Josh. Here's his phone number. Well, no, you want to be careful about that. But translating things into meaningful terms so it's less scary for real users can be very beneficial. Number 2, handle as soon as possible. Try to handle, if you can handle it close to the source of the error, that's great. Don't just assume somebody up there is going to handle it. Probably have at least one high-level exception handler so the system doesn't just bomb out with the default error message for a stack trace. It actually should have some sort of high-level message that deals with any cases that aren't handled, so the user doesn't see the gory details. Right. So don't just throw on exceptions for things that can be reasonably handled, or for things that can't be reasonably handled. Try to do what you can. If you can handle it reasonably well, try to do so close on, and don't just throw it. You might want to, in the exception itself, document the cause, say where it occurred, what it was in the middle of doing, that sort of stuff, and eventually, include relevant contact in here. finally, and this is important, we may have a lecture on this. Hoping to put together a lecture on this. Try to make things atomic. What do I mean by atomic? That may sound scary. What do we mean by make operations atomic? It has to do particularly with error handling. Anyone? What does it mean to be atomic?
The operation completes before another operation is begun.
Okay, good. That's often associated with the acid properties, and to actually make it more specific, it's closely related to that. It as far as anyone outside is concerned, it either is complete, or it's as if it's never happened yet. Okay, so it doesn't get halfway through and bomb out in some incomplete state. If it gets halfway through and an error occurs, either it corrects for it and goes forward and completes, or it backs up to the original state. It doesn't leave it halfway done, half-baked. How many people have heard this notion before in a significant way? Okay, yeah, a couple people here. So ladies and gentlemen, it's no exaggeration to say that that the services you use over the World Wide Web depend heavily on this notion. So if you're ordering a book at Amazon and you're halfway through the process of paying for it and something happens, they can't deliver on your book, you don't want it to charge you and then just say, well, the book's not available, sorry. Right? You want it to either charge you and send you the book, or say, okay, we don't have the book, sorry, not charge you. Does that make sense? It either completes the whole package, the whole transaction completes, or it's as if it never happened. Everything's rolled back to the original state. Do you see why this is so important? And this gets critically into this issue of corruption. You don't want a file half-written overwriting the previous file halfway, and then your system bombs out because there's some error that it got. Maybe it ran out of disk space, maybe it ran out of memory, maybe it's a programmer error, and it bombs out halfway through. That would be bad. It didn't get all the way through, and it's not back at its original state. It's overwritten its original file halfway. That could be extremely bad. That's negative value delivered to the user. Not only do they not have the results they were expecting, it's destroyed value. You understand that? Yeah? Okay, so ladies and gentlemen, when we're trying to handle errors, we aspire to make it atomic. In other words, if something goes wrong, we don't like it, that's okay, but we try to make it as if nothing had changed from its original state. We back up what we were doing enough so that we haven't changed something out from the user. So we're never in the situation where we've corrupted it, where we've destroyed value, half overwritten something, etc. And ladies and gentlemen, as I say, the World Wide Web, all these e-commerce sites, Amazon, for example, they depend, it's hard to overstate how fundamentally they depend on this notion of atomicity. And how many people are in 355 right now? So you'll hear in that class, if you take it, discussion of the so-called acid properties, atomic, consistent, independent, and durable. This is what allows databases to function so centrally in a robust fashion. If something goes wrong, they can roll back automatically. It's beautiful, ladies and gentlemen. You connect to a database, you go, do that, change this other thing, all in one transaction. If something goes wrong, you say, roll back. It just undoes all that. Pristine. It's back to its original state. Or you get all the way through, things are hunky-dory, and you say commit, and it commits it. And even if the disk crashes in the middle of the commit, get this, and there's no exaggeration, the disk crashes in the middle of the commit, it will either be totally finished or back to the original state. I don't exaggerate. It's planned that carefully. It is that important a property. So, when it comes time to sending these records of the surveys collected back to the mythical server, Postgres or otherwise, either the survey should be sent totally, or it shouldn't be sent. Hassan should never have to look at a halfway created record back on his server. Does that make sense? You see why that's so important? And by the same token, the little, the handheld system that's sending these off shouldn't wipe away that record until it's sure it's been transmitted in full. Yeah. So this issue of atomicity is important for error handling. Okay. And in your cases, I know it's hard. And in databases course, you'll see the databases give you this essentially for, not quite for free, but it's built into Postgres. It's built into MySQL. You can create atomic operations. And this is why people love using databases. It's not the only place you can get atomicity. Try in your code. If something goes wrong, try to back up so the situation as if you never started the changes. Make sense? Okay. Okay. Final thing I'm just going to start talking about is assertions. We've talked about return codes. Return codes are great for common events. They don't have common special language support. They're lightweight. And with enums, for example, they can be fairly clear, quite careful, but you still can't pack too much information into them, for example. Nothing's going to force you to handle all cases. Exceptions, the compiler can say, hey, you haven't handled this exception. You handle it, or you tell other people you're not handling, and they have to handle it. Right? The compiler does support them explicitly. You check these sort of things. You can pack all sorts of information in them, but they're kind of expensive if it's happening a lot. And so it should be sort of unexpected, fairly rare events. You don't want these exceptions firing off, 100 times a second or something like that. You want to use them, for things that are less common than that. Let's talk about assertions. What are assertions used for? They're used to capture. Assertions, ladies and gentlemen, mark my words. Assertions allow us to document and check operationally our assumptions about code. They allow us to be explicit about what we're counting on what we're relying in terms of our exceptions. And we put in assertion statements to check those things, and if something goes wrong, it will return an appropriate error message. These things should never happen. It should be like, this is a situation where we know that we should never have a non-negative value for this index into the array. And suddenly we see a negative value here. Must have been some programming mistake. Somewhere we did I minus minus and we shouldn't. There's a programming error. It should never happen logically, but it is there. And the assertion catches it. We created the square root routine and we state nobody should ever call this with a double value that's less than 0. And guess what? We tell them, do not call us with a double value less than 0, and guess what they call us with? There's a programmer error. They ignored the specification. We capture it with an assertion. Ladies and gentlemen, what I what is not appropriate is you catch an out-of-memory error with an assertion. Catch a situation where new returns null because it's out of memory. Why isn't that okay? Yeah, it could happen. I mean, it's a perfectly legitimate thing. It has nothing to do with a user mistake. Oh, sorry, a developer mistake. It has everything to do with a situation that's inconvenient, rare, but we got to be able to handle it. We can't just say, we're not going to handle this, buddy. Back to you. That's not legitimate. Assertions should document things that should never happen. If something's happening of this sort, things are insane, and the programmer needs to know about it to remove some bug. There's no bug that's necessarily required if we're out of memory. Some bug, it can perfectly well happen on a user machine. So assertions are used to catch logical errors, developer mistakes. They should never occur, but we put them in there just in case we've made some mistake in our reasoning. Because we do make mistakes. There's special language support for them. They appear in debug code. Sometimes they appear in user code, but a lot of the time they're stripped out of user code. We strip them out because the thought is that they're useful aids in debugging, but they should never be encountered when the user is actually running the code. It's debugged enough. Some people argue they should stay in there, and they could still do something like say, okay, I discovered this error, let me send a message back to the company server and then bomb out of here. And assertions are part of the general philosophy of what's called offensive programming. You try to get a program to fail early and fail hard. If there's a program that's broken, you want to know about it as soon as possible. You want to know that as early as possible something's wrong. And they are one technique, and probably the most popular technique. They're extremely common. And they're one technique for getting it to fail early, fail hard. If there's a problem there, you don't want it to stay silent and deadly while you're running this program. You want it to fail in an obvious way so that you know that problem is there, so you can go fix it. You want to fix the mistakes that are present, not allow them to stay hidden. There's other techniques like this too. You fill memory with that's been recently allocated with illegal values, or fill it with illegal value just before it's deleted, for example. In C, there's a whole set of different techniques you can use to prevent memory errors. But here, our goal is to fail early, fail often. Okay, but there's lots of other benefits too. You document assumptions, you reduce the likelihood an error will slip through, it reduces debugging time, and it can help improve thoroughness of tests. Let me give you a glimpse of what this looks like. So this is what it might look like in Java. So here we have a method, and it takes some arguments, and there's some precondition. Either the first array and the second array are equal length, or both are null. And here we can actually check in the assertion, okay, is this true? Either they're both null or they're of equal length. You put in an assertion, it checks, for example, these preconditions. But that's not the only case in which we check preconditions, or we use assertions. We may call off to a routine, and our understanding from this method that we've called is that it should never return null, and we'll test that it's not returning null. Maybe we have a data structure. Every item in the data structure, it always contains ints, and they should be 1 or above. And we'll confirm that this one we get out of this array is 1 or more. Or maybe we're dealing with a situation where this certain value should only be increasing over time, and we'll make sure that its value before the call and after the call, that it's only gone up, something along those lines. These assertions are extremely common in certain types of code. Ladies and gentlemen, let me inveigh upon you, exhort you, plead with you. When you're writing code, you should be reflecting on what my assumptions are. So what's the case here? What can I assume? Do I know this is non-null? Do I know that this array has been filled in already? Do I know that this value that's been passed to me is greater than 0? Do I know that every item in this hash table has a non-null value associated with it, or that the key is non-null? Those are all assumptions that will sort of go through in our head when we're writing code. Right? We reason through, like, what's the current situation and figure out what to do. Does that make sense? And when you do that, just reflexively write it down in an assertion. Just write an assertion of that thing. While it's in your mind, just write it down. And what's the basic syntax of it? The basic syntax is you say assert this certain expression. This is some Boolean expression. You know, P not equal to null, for example. Right? You put in parens to make it clear. This could be some function call. You know, is alive, and you pass it a certain reference. It could be anything. It could be some Boolean expression. Colon, and this is the error message that you'll return if it's false. Okay? If you want to make sure that the code never reaches this certain point, what would you do? Suppose you had some piece of code and you want to make sure it never reaches this point. What would you assert? False. Illegally reached, end of binary search, without finding the thing looked for or whatever, right? Litter your code with these. The more of them I see, the happier I'll be. It's really easy to do. Get in the habit of doing it while you're writing this code. This will end up helping you a great deal, because sometimes you'll find, what? We ended up there? We should never have gotten there. If you're debugging the code, this will be a big help to figure out where it's going wrong. It documents to someone else what your assumptions are, that they should never reach there. Makes it very clear what's going on. So, ladies and gentlemen, please use assertions. Do not put side effects in them. Why not? Do not have a side effect in the middle of assertion. Why not? Because, ladies and gentlemen, they often get stripped out of the code. In Java, you could simply say, as part of the when you're running code, so Java some jar file or what have you, foo.jar, you can have minus disable assertions, or minus DA is the short name for it, and it disables all the assertions in there. Okay, so that's all for today. We've seen 3 ways of handling things. I have a bunch of examples, and I'll show you how you enable them or disable them here in Java, either on a per module basis or in general. And you can go and look at some additional cases, for example, here, where we're using assertions in various places. These are best practices. Please use them and know where each gets used. Okay? Thanks.